So here's what I'd like to do today. I'd like to consider the graph f of x equals x squared, and I'm just going to look at the first quadrant portion of it. Okay. And then let's say here's the point right here, 1, 1. And let's pick another point on the graph. Keep it simple. Let's say 2, 4. All right. I'm going to start with the point 1, 1, which technically is 1, f of 1. And this point is 2, f of 2. And what I would like to do is compute the slope of the secant line. Now, in case you're not familiar with the vocab, the secant line is the line passing through the 2 points. That's it, all it is. Okay, that was a terrible line, but you got the idea. I'm going to have that line right there. So the way we would write it is the slope of the secant line. Now, from remedial algebra, the definition of slope on the xy plane, the definition, slope is defined to be the change in y over the change in x. And by the way, that is actually the formal definition. We use the deltas, change. What's the change in y? That's the difference of the y coordinates. What's the change in x? That's the difference of the x coordinates. Oh, okay. So in baby algebra, we might say y2 minus y1 over x2 minus x1. Exactly the same thing. Doesn't make any difference. So what is this? Well, this would be f of 2 minus f of 1 over 2 minus 1 in this context right here. And then that would be what? That would be 4 minus 1 over 2 minus 1, which of course is 3. Okay, great. Now here's what I'd like to do. I would like to move closer to 1, 1. So let's take a value that's much, much closer. How about, let's say right about here, this would be, let's say 1.2 comma f of 1.2. I don't feel like calculating that quite yet. And I want to find the slope of the secant line that passes through these 2 points. Well, I think that slope is not going to be as much. So let's find, I'll number these. So now my second secant line is going to be f of 1.2 minus f of 1 over 1.2 minus 1. Well, what's f of 1.2? Well, that would be the square of 1.2, which would be 1.44 minus 1 over 1.2 minus 1. So if I do a quick check there, that would be 0.34. And that doesn't, hold on a second. Did I do that? 1.2. Oh, over 0.2, sorry. So 0.34. God, I can't even, 0.44, sorry. I might get, my math is subject to how much coffee I had today. Clearly not enough. That's 0.44. There we go. Over 0.2. And what would that be? Exactly 2.2. Sorry about that. Total brain fart there for a second. Now, okay, that's not really surprising. Now what I want to do is get even closer to 1, 1. I want to get really close to 1, 1. Now, how close do I want to get? Well, let's say I'm going to point right there. Let's call that 1 plus delta x, or delta x will represent a small change. See, right now the delta x would be 1. Right here, the delta x would be 0.2. Let's just say delta x is really small. It's not 0, but it's really small. So now I want the point 1 plus delta x comma f of 1 plus delta x, and I want to find that secant line, which probably should be even a little bit less. So let's do it one more time. So my third one is going to be f of 1 plus delta x minus f of 1 over 1 plus delta x minus 1. Well, that makes my denominator pretty easy. It makes my denominator just delta x. What's my numerator, though? Well, 1 plus delta x, I'm going to input here and then square it. So that would be 1 plus 2 delta x plus the square of delta x minus 1 all over delta x. So that would give me 2 delta x plus the square of delta x all over delta x. So clearly I can factor and cancel a delta x. And when I do that, I'm going to get 2 plus delta x. Oh, okay. Well, let's see, that seems to agree with the previous problems, because in this case, my delta x was a 1 and my answer is 2 plus 1. In this case, delta x was 0.2 and my answer is 2 plus 0.2. So if I said, move on this parabola to any other point on the parabola and call the change, just call it delta x, I could actually tell you the slope is just 2 plus delta x. So now here's the last question. What about at the point 1, 1? At the point 1, comma 1, I would like the slope of the tangent line. So in other words, if I have a curve like that and I want the slope here, I want to do that. I don't want to involve a second point. So that's what the tangent line is. There's no second point. Okay. Now, a lot of folks get a little bit confused on what a tangent line is. I like to think of a tangent line as I'm moving on the road. It's when you hit the banana peel, which way would you slide? That might sound corny. That's absolutely the correct interpretation of a tangent line. So when I hit that banana peel, I don't slide on a curve, I slide on a line. So the slope of the tangent line, well, how do I get the tangent line? Have delta x get smaller and smaller and smaller. In fact, take a limit. So the last thing I'm going to write then the slope of the tangent line would then be the limit as delta x approaches 0 of f of x plus delta, in this case, sorry, 1 plus delta x minus f of 1 all over. Now, I don't need to say 1 plus delta x minus 1. That already is delta x. So I'll just write delta x. And I think we can all see what's going to happen. It's the limit of this. We've already done the algebra once, so I'm not going to repeat the algebra. So this would be the limit as delta x goes to 0 of 2 plus delta x, which would simply be 2. Cool. So I can tell you now that the slope of the tangent line on this parabola at the point 1, comma 1 is simply 2. Great. Now, what if I wanted to find the slope at another point? What if I wanted to find the slope at 10 different points? See, this is now a physics class. So in a physics class, the common thing you would do is you do multiple calculations of something of this nature. Okay. I like to liken something like this. Okay. I've got the ramp. I've got the little Pinewood Derby. Remember those things in Cub Scouts, and I'm racing it down and I want to figure out how far it's moved every 10th of a second, maybe 40, 50, 100 calculations. Then I can go back and compute things like velocity. It's tedious, but in a physics, you're going to do multiple calculations along the way. If I've got to solve and rederive something from scratch every single time I compute it, that's really inefficient. What if we figured out a way of saying, let's find the slope of the tangent line to this parabola at every point on the parabola as a formula? Then I can say, now, what is it when x is 1? What is it when x is 2? What is it when x is -3? That would be way more efficient if I had to do this process multiple times. So let's do this now. All right, so let's find the slope of the tangent line. I'm starting to do more erasing here. Of f of x equals x squared at every point. Okay, well, how do I do that? Well, I do the same process. I just don't evaluate it at 1. I leave it as an x. Well, again, what is the slope? It's the change of y over change of x. If y equals f of x, then the change of y must be f of x plus delta x minus f of x. This is an absolute. This is true throughout mathematics. That's never going to change. The change in y is the difference in my y coordinates when I've changed in x. So just sort of for a generic graph, if I'm at a point x comma f of x, and I move delta x units, and now I'm at a new point, call it x plus delta x comma f of x plus delta x. Okay, we all understand this. I have some curve that's passing through these 2 points. This is one of the points. I'm going to move delta x units to the right. So therefore, there's my new y value. The difference in the y values is called delta y. The difference in the x values is called delta x. And then the slope is simply the ratio of delta y over delta x. But when I'm using f of x notation, that requires that I write something like this. So we can then say the slope of the tangent line is equal to the limit as delta x goes to 0. Basically, the slope of the tangent line by definition is the limit of the secant line. And the secant line is just the classic delta y over delta x. Some people remember it as rise over run. Same thing. There's no difference. The only difference is now is I'm taking a limit at the end of the process. So we're going to write it right here. Now, without the limit, if I'm just looking at that, some of you remember doing things like this in pre-calculus. This is often referred to as the difference quotient, which is a really, really ambiguous title, difference quotient. I mean, I could write an infinite number of quotients that have differences. This particular one we practice a lot. In fact, it's on the algebra review that I posted. I ask a question of this nature, because this is the slope of the secant line between any 2 points on a function. This is the slope of the tangent line at any point on a function, because I took the second point and I just moved it closer and closer and closer and closer until they are 1. So in this example here, for y equal x squared, or for f of x equals x squared, we're going to get the slope of the tangent line to be the limit as delta x goes to 0 of, now what do? I'm replacing x with x plus delta x. Okay, minus f of x over delta x. Now, do a really quick check. I cannot replace delta x with 0, because that would mean on the top I have 0 and on the bottom I have 0, because you're finding the slope at the same point. Oh, so I have to have the second point and move in, get closer and closer. So delta x is never 0. I'm taking the limit. So what I'm going to do is expand this and manipulate this algebraically. If done correctly, then every term that doesn't have a delta x in it should cancel. And I should be able to evaluate the result. So this is the limit as delta x goes to 0 of x squared plus 2x delta x plus the square of delta x minus x squared all over delta x. Well, I can certainly do that. So this is 2x delta x plus the square of delta x all over delta x. Now, I cannot evaluate yet because I still have a delta x on the bottom. That, as I affectionately call it, that is my problem child. I need this guy gone. I can't evaluate this as long as there's a delta x in the bottom, because that means I'd have a 0 in the denominator. But at first glance, you notice each term has a delta x in it. So I can factor and cancel those delta x's. And my numerator would then be simply 2x plus delta x. I don't need to write over 1. I've already canceled them. Now, at this point, that's no longer an indeterminate form. I can clearly evaluate this as delta x goes to 0. I just got 2x. Oh, so that means on a parabola, at every point on the parabola, the slope of the tangent line is nothing more than double the x coordinate. Does that agree with what we just did? We just did y equal x squared, and we used the point 1, 1. Well, 2 times 1 is 2, and we got a slope of 2. Another way of thinking of this is, right, so we did this. Well, what if we'd taken a negative x coordinate? This says we would have had a negative slope, and that makes perfect sense. In fact, the further we go to the right, doesn't this get steeper and steeper and steeper and steeper? So our slopes are getting larger and larger. And the best part is, what about the vertex? Right where I turn around, wouldn't the tangent line be horizontal? So when x is 0, I should have a horizontal tangent line. When x is 0, my slope is 0, which means it's horizontal. Beautiful. So we just figured out a way to find the slope of the tangent line at every point on this curve. So we're now going to give this a formal definition, okay? And with formal definitions comes lots of tedious notation. All right, we're going to define this is called the definition of the derivative. Okay, the derivative of a function. So first is if y equals f of x, d dx is called the differential operator. It is not a quantity, it's an instruction. Kind of like if I put a square root symbol, or if I put natural log, or if I put cosine, if I put limit, it's always of the thing that follows. So d dx means you're going to take the derivative with respect to x. X meaning the independent variable. By the way, we could take derivatives with respect to any variable if we choose, and we will. Within a week or two, doesn't matter what it is, you can take a derivative with respect to every variable you can think of. So d dx means I'm going to take the derivative with respect to x, which makes sense because that's my variable. And we write it like this. d dx, first of all, of y, we write as this, and we say it dy dx. That's how we actually pronounce that statement. d dx is one symbol. You don't cancel the d's. It's not that. d dx is a symbol. It's an operator. It is an instruction. d dx doesn't equal anything. d dx of my function equals something. When I do d dx of y, the notation we use is dy dx. When we do d dx of f of x, because I'm using function notation, then we write f with a little slash here, and we read this one f prime of x. We read this one dy dx, we read this one f prime of x. They are exactly the same thing. The reason for two notations is, did I define my function as y equal x squared, or did I define my function as f of x equals x squared? So you answer the question based on how it's defined. The majority of the time, we actually use this notation, okay? But sometimes we use this, and they're essentially interchangeable, okay? You're not going to change the meaning. But if I wrote y equals, you wouldn't say f prime. And if I wrote f of x equals, you wouldn't say dy dx. You'd just say that. So that's the notation. We'll go further in a moment. So now, the definition of the derivative, if y equals f of x, then dy dx, which equals f prime of x, is equal to the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x. This is the definition of the derivative. In other words, what we just did a moment ago to find the slope of a tangent line is also what we're going to call the definition of the derivative. This will be the most used limit basically from now until the day you die. You will do this more than any other type of limit because almost every formula we derive in calculus comes from here. Okay, we want to find the derivative of any particular function. We generally start with the definition of the derivative, we manipulate the limits, and then we get an answer. It's really cool stuff. So then we just did this. We said f of x equals x squared. Therefore, f prime of x equals 2x. That's what we just did a moment ago. This is the formal way of saying it. Kind of cool. Okay, so let's do this for another one. Let's do this for something a little more complicated. Like I said before, we're going to develop rules. You're actually going to develop rules to find the derivative of every function that exists. And we'll be doing that just over the next few weeks. That's not something you're going to do over several semesters. We're going to do that over the next month, essentially. All right. So for f of x equals, let's say, the square root function, let's find f prime of x. Okay. So I want to get you used to using the formal notation. And the key is whenever you hear the term definition of the derivative, that means you're going to do that limit thing that we just did. So I'm going to write f prime of x is equal to the limit as delta x goes to 0 of f of x plus delta x. So I'm going to replace x with x plus delta x minus f of x all over delta x. So now I'm looking at this thing, and that looks kind of scary because I can't cancel anything. I can't factor anything yet. In fact, delta x is the problem child, and this delta x lives inside a square root. Oh, darn. What can we do? Well, actually, we've already taken a limit of this form. You did this on the first quiz. I need the delta x out of the root. So what I'm going to do is multiply numerator and denominator by the conjugate. So I'm going to multiply, and we know this is legal because I'm basically multiplying by 1. Okay, that's always legal. If I said multiply top and bottom by 10, multiply top and bottom by 3x, I'm multiplying by 1, so there's no issues. But what this does is this gives me a numerator that I might be able to actually work with. So on top, remember, a minus b times a plus b is a squared minus b squared. So I have the root squared minus the root squared. So there's my numerator. That's why you chose the conjugate, because again, a minus b times a plus b is this squared minus this squared is my result. On the bottom, I have delta x times x plus delta x under the root plus delta x. I don't want to distribute here. The reason is I want to be able to cancel. If I distribute, I will lose sight of the thing I'm trying to cancel. So if you notice here, algebraically, if I drop the word limit, is this quotient equal to this, and is this equal to this? Yes. Okay. Now I'm going to cancel these guys because that's my problem child. The thing going to 0 is the thing you must cancel. So my numerator is a 1. My denominator is a root x plus delta x plus root x. Right now, this is no longer an indeterminate form, so I can evaluate. As delta x approaches 0, that term is just becoming root x. So I have 1 over root x plus root x. So my limit would be this. Beautiful. So if I'm looking at the square root function, then we would say the derivative at every point on the square root function would look like this. Now, at first glance, is that right? I mean, does that make any sense? Well, let's look at a picture. I find pictures at this point can be really useful. Alrighty. So if I drew a picture of the square root function, it looks something like this. We know basically it's the top half of a sideways opening parabola. So as x gets bigger and bigger and bigger, what's happening to my tangent lines? They're getting less and less and less steep. As x gets bigger and bigger and bigger, the slopes are getting smaller and smaller and smaller, always positive. But now here's an interesting thing. As I close in on 0, what's happening? Well, let me give you a hint. Since this would technically turn around, wouldn't the tangent line at the vertex there, wouldn't that be vertical? A vertical tangent line, is that even possible? Yeah, actually, we're going to look at those a lot. So at the origin, my tangent line would be vertical. And what is the slope of a vertical line? Undefined. By the way, if I try to put an x equals 0 in, what do I get? Undefined. So that does agree, doesn't it? And when I'm only a little tiny bit away from 0, I should have really steep tangent lines. When x is really small positive, this is a large number. So yeah, that actually does agree thoroughly with the picture. Now, I didn't need a picture to do the math, but I definitely needed this. Now, that's the definition of the derivative. But the problem with the definition of the derivative is the algebra. The algebra can be very intense. You see, what if I said, I want you to find the derivative of something more complicated? So here's how we often would say it. here's what we just now said. We just said d dx of the square root function equals this. This is formally what we just said. That's our conclusion, right? We did all the work already. This was the question. This is the answer. And we needed to do the definition of the derivative. What if I asked you to do something like this? I want you to take the derivative of x to the 10th power. Okay, great. Except that means in the definition of the derivative, I would have an x plus delta x to the 10th power. And I'd have to expand all that. And then I'd have to do all the algebra. That would be nightmarish. Forget 10. What if it's a 1000th power? What if it was the 3/2 power? I mean, how do you expand something? Yeah, so there is a problem there. What I showed you algebraically is absolutely always true, but realistically, you can only manipulate it when things are small. Otherwise, it's just too big. So I'm going to show you the first major shortcut in a moment. The first thing, though, I want to do is establish a couple of major rules with limits. Now, we know, or with derivatives, sorry, we know something about limits. We know that the limit of a sum is the sum of the limits. We know that a limit of a scalar multiple is a scalar multiple of the limits. We know that, in fact, in the TAN book, he actually does beautiful epsilon delta proofs. That's one of the reasons you want to know epsilon delta. That validates those two limit properties. So here's my question. What if I wanted to do the following? I have two functions, let's call them f of x and g of x. And I wanted to take the derivative of their sum. Now, if f of x is not very complicated, I could do the definition of the derivative. If g of x is not very complicated, but if I'm putting them together and then trying to simultaneously do both of these, that could be really, really difficult. So let's see what this would look like. This would look like the limit as delta x approaches 0 of f of x plus delta x plus g of x plus delta x minus f of x plus g of x. Can I squeeze it in there? Okay, barely. Okay, that's what this would be. Okay, if I replace x with x plus delta x, then I have this minus this. That looks just downright scary, but remember, this is a limit now. The limit of a sum is the sum of the limits. So can I rewrite this? Can I manipulate that? Think of distributing that negative sign. Could I rewrite this as f of x plus delta x minus f of x plus g of x plus delta x minus g of x? Now stare at that for a moment. If I distribute the negative, I can always pull apart a quotient. So if I said, can you put these two back together? Yeah, as long as the denominator is the same, you'd add numerators. So algebraically, cover up the word limit. Algebraically, that quotient is absolutely guaranteed to be the sum of these two quotients. Okay, so now what? Well, I'm pretty sure this quantity right here is the definition of f prime of x. And this quantity right here is the definition of g prime of x. So we're done. We just proved a very, very powerful thing. We just proved that the derivative of a sum is the sum of the derivatives. So that would mean if I'm taking the derivative of a whole bunch of things being added together, like a polynomial, it's equivalent to just taking each derivative one at a time. I don't have to look at it as one big giant mass that I have to deal with simultaneously. I can deal with everything one at a time, which is extremely practical. Okay. Now, second rule, and the only other absolute rule that I'm going to go over today, what if I want to do the derivative of k times f of x? K being any constant. Well, I know this is going to be the limit as delta x goes to 0 of k f of x plus delta x minus k f of x all over delta x. Okay, that's straight up definition of the derivative. Well, how does that help me? Well, remember, I can factor constants out of a limit. I can always factor a constant out of a limit. So this would be the equivalent to k times limit as delta x goes to 0 of f of x plus delta x minus f of x over delta x. And why is that good? Because the quantity on the right is f prime of x. Cool. So the derivative of a sum is the sum of the derivatives. The derivative of a scalar multiple times a function is the scalar multiple times the derivative. Those are going to be the most useful and used rules that you ever do with derivatives. And you notice they both come directly from limits. That's one of the reasons the limits are so important. So today we've already done this. We did the derivative of x squared is 2x, and we did the derivative of root x is 1 over 2 root x. What if I wanted you now to do the derivative of, let's say, 3x squared minus 4 root x? Just throwing something out at you. Oh my gosh. To go back to the definition of the derivative and do x plus delta x and all these, and you realize how gnarly that would be, and trying to expand this and figure out what to multiply top and bottom, this would be horrible. Except we now know this is 3 times the derivative of x squared minus 4 times the derivative of root x. That's what we just proved. The derivative of a sum is the sum of the derivatives. The derivative of a scalar multiple is the scalar multiple of the derivatives. So this would simply be 3 times 2x minus 4 times 1 over 2 root x, which you could then simplify if you chose. Now that is handy, because more often than not, when you take derivatives, you're going to take derivatives of lots of things, not necessarily one thing at a time. Now, the only derivatives I know today are x squared and root x. I kind of like to know more. So we're going to derive some very, very powerful things in general. I'd like to be able to take derivatives of polynomials and trig functions and all sorts of things. Well, over the next few weeks, we will derive every rule there is. So first, I'm going to do a little bit of algebra review, because there's a thing that I'm going to use in a little bit, an algebraic rule that might be a little obscure. Okay.
Professor?
Yes.
Sorry, I think I missed it when you explained it. Why is the derivative of x squared 2x?
Well, that we derived it. We did the whole expansion.
Oh, and then
It took us about.
that was a silly question.
Well, no, remember we started with y equal x squared, and we did the derivative at a specific point, 1, 1, and then we did it in general for the whole parabola.
Yeah, we actually did that. Okay.
Yeah, I'm not telling you the derivative is 2x. We actually discovered it. Just like we discovered the derivative of the square root function was 1 over 2 root x. I didn't tell you that. We just did the limit, and that's what we got. Now, the definition of the derivative is how we get all derivatives, but it is impractical to go through this process every single time. So what we're going to do is use the definition of the derivative on functions in general to come up with that function's derivative. Like, for example, we're going to come up with the derivative of the sine function. We're eventually going to come up with the derivative of all trig functions, of e to the x, of natural log of x, of the hyperbolic functions, of the inverse trig functions. Everything we can consider, we're going to find the derivative as a formula, as a rule. So once we use the limit to get the formula, we won't need to use the limit further. We used epsilon delta to justify the limit. Now we don't need to use epsilon delta to prove that we're doing limits correctly. So consider the following. We've got a plus b to the 0. I've got a plus b to the first. I've got a plus b to the second. This is called the binomial expansion. Okay, I'll just do a few of these. You, in a pre-calculus and hopefully in an intermediate algebra class, you did stuff like this. So you said, well, this is 1. This is a plus b. This is a squared plus 2ab plus b squared. This is a cubed plus 3a squared b plus 3ab squared plus b cubed. I'll just go this far. And then 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the fourth. This goes on forever and ever and ever and ever and ever. It's called the binomial expansion. There's actually a formula then, because eventually, what if I wanted a plus b to the nth power for any positive integer n? Well, if I look at the coefficients only, you notice that the coefficients have a pattern. 1, then the next one is this, then the next row is this, then the next row is this, then the next row is this. Now this goes on forever and ever and ever, but there is a very clear and simple pattern. Does anybody remember what we call this expansion? You would have done this in algebra and pre-calculus, I would hope.
Pascal's triangle.
Pascal's triangle, exactly. It's called Pascal's triangle. And there's a whole lot of cool things. For example, any position is always the sum of the numbers above it. That's always true. So if I said, what is the expansion for a plus b to the fifth? 1, 5, 10, 10, 5, 1. Oh, so I want you to do the expansion of a plus b to the 1000th. Does that mean I got to find all of the things that preceded it? Well, that would be very inefficient. Okay. If I don't want to have to produce all of this to find the next one, I'd like to know what is the next one. And so once we are aware that there actually is a clear identifiable pattern, I don't ever want to have to do the triangle. I want to just be able to say a plus b to the power and then write it out. That would be far more practical. So now that I understand that, what are the coefficients exactly? Well, it turns out the coefficients involve factorials. And some of you guys remember this. This is the only part of this course, by the way, where we're ever going to talk about factorials. Calc 2, it's a major, major concept. So what is this? Does anyone remember? It's n. No, it's not. It's n really loudly. No, this is called n factorial. And this is equal for a positive integer n, this is equal to n times n minus 1 times n minus 2, right? 3, 2, 1. So if I said 5 factorial, that's 5 times 4 times 3 times 2 times 1, or 120. Factorials are the fastest growing things there are. Nothing grows faster than a factorial. If you have just a standard scientific calculator, you can go up to 69 factorial on your calculator, but the moment you hit 70 factorial, it'll say error, because 69 factorial is on the order of 10 to the 98th power, but 70 factorial is on the order of 10 to the 100th power, and your calculator won't keep track. Now, I've got a TI-89 Ti Titanium. I can go 449 factorial on mine, which is on the order of 10 to the 999th power. That's how fast they get. But that's not important, okay? I need to know what that is. And by the way, 0 factorial is actually equal to 1. It's not 0. If 0 factorial were 0, that means all factorials are 0. No, factorials stop at 1. 0 factorial, then what is 0 factorial? Well, it turns out factorials come from something way, way bigger. It comes from something called the gamma function, which you will see in the differential equations class. And it's actually calculated. It's a strange thing. So where factorials are used, particularly, now, if you've had statistics, you are very familiar with things like permutations and combinations. At least you should be, because you do that heavily in statistics. So I'm going to introduce you to something called the combination. We need this only for the next thing. Combination of, we say n, choose r. I have n objects that are different. I'm going to select r of them. R is less than or equal to n. You know, if I've got 40 people in the class, I can't select 50 of you, but I can select 5 of you, 10 of you, or all 40 of you. In fact, I can select none of you. A combination of n choose r, that's how we actually say it. It's written this way, n, r, and parentheses around it, not a quotient. And this is equal to n factorial over n minus r factorial, r factorial. This is the formula for what's called a combination. Many of you have seen this. In fact, the funny thing is, in an intermediate algebra and a pre-calculus class, you're supposed to learn this, but your class may have skipped it. If you've been in stats, you did this for a whole semester. So most of you have seen something like this. I don't need you to be the master of this. I just need you to be aware of this. The combination, as it turns out, is the coefficient of every term in the binomial expansion. So when I did, let's say, a plus b to the 4th power, right? That was a to the 4th, which is the same as saying 4 choose 0, a to the 4th, b to the 0, plus 4 choose 1, a to the 3rd, b to the, a to the 3rd, b to the 1st, plus 4 choose 2, a to the 2nd, b to the 2nd, plus 4 choose 3, a to the 3rd, a to the 1st, b to the 3rd, And then finally, 4 choose 4, a to the 0, b to the 4th. This is exactly what we did when we did the binomial expansion. Oh, so I don't need the Pascal's triangle, all the numbers in Pascal's triangle. So the row that we did for a plus b to the 4th, the row was 1, 4, 6, 4, 1. Now you notice 4 choose 0. I have 4 people in the room. How many ways can I choose 0 of them? Well, there's only one way, and that's to not pick any of them. I've got 4 people in a room. How many ways can I pick all 4 of them? Well, there's only one way, and that's to pick all 4 of them. I have 4 people in a room. How many ways can I pick just one of them? Well, there's 4 different ways I could do that. So I have 4 people in a room, call them people A, B, C, and D. I can go A, B, A, C, A, D, B, C, B, D, and C, D. That's 6 of them. So you can argue this from many points of view, and you'll always get the same result. Notice 4 choose 0 is 4 factorial over 0 factorial, 4 factorial, according to this formula, which means 0 factorial actually has to equal 1, because we just said this quantity is 1. So that's a nice little feature. Now I'm showing you this because when I do an expansion in general, this comes up. So here's what we're going to do next. We're going to derive one of the most useful formulas early on in calculus. For positive integer n, and another way of saying that, I'm going to introduce you to some formal notation. In an upper level class, capital Z is the set of integers. Z plus is the set of positive integers, also called the natural numbers. It's the same thing. So some textbooks will say n is an element of the natural numbers. I'm saying n is an element of the positive integers. I don't need you to know that notation. I need you to be aware that it exists, because the further you go in math, the more common notation like that is going to be in a problem. So in words, for positive integer n, we want to find the derivative of x to the nth power. Now, we just did it a few minutes ago for x squared. What if I want x to the 100th? What if I want x to the millionth? What if I just want x cubed? Yes, I have to do the expansion of the definition of the derivative, x plus delta x raised to that power, and that can be large. So we're going to actually derive this right now, and we're going to create a formula as a result. So this is the limit as delta x goes to 0 of x plus delta x raised to the nth power minus x to the nth power over delta x. That's the definition of the derivative. Now, just to make it easy on us, let's assume n is really large. That makes it easy on us. Yeah, we want to cover all of our bases. We've proved it for n equals 2. Let's suppose n is really large. So then what does that mean? It means I'm going to expand the numerator. And this is going to become x to the n plus. Now, in the binomial expansion, what was the next term? Remember, it's always n choose 1, which is just n. X to the n minus 1 delta x to the first power. Think of these like the a's and b's. And what's the next number? Well, the next number is n choose 2. This would be n choose 1. That's 1. The next one I'm going to write n choose 2. X to the n minus 2 times the square of delta x plus, now, bunch of terms with delta x cubed or higher. That's what's next. See, what's the next term going to involve? X to the n minus 3 delta x cubed. Then the next term will be x to the n minus 4 delta x to the 4th. All the way until I get delta x raised to the nth power. I said assume n is large. Then what? Then minus x to the n all over. I know that looks kind of sloppy. Okay, all over delta x. I don't need to write forever and ever and ever, because what's going to happen is a lot of the terms will end up going away. The only term without a delta x in it is the x to the n, and that just canceled. So now I've got the limit as delta x goes to 0 of nx to the n minus 1 delta x plus n choose 2 x to the n minus 2 times, sorry, this is getting a little cramped, squared plus bunch of terms with delta x cubed or higher. How's that? All over delta x. So here's what you notice. Every term in the numerator, every term has a delta x. Okay, delta x to the first power, delta x to the second, third, fourth, fifth, it's all the way up to delta x to the nth power. I can now factor and cancel all the delta x's out of every single term, and then I will no longer have a quotient. I will now have, what will I have here? Nx to the n minus 1 plus n choose 2 x to the n minus 2 times a single delta x plus bunch of terms, but no longer delta x cubed or higher. Now it would be delta x squared or higher. Okay, we're ready. The expansion of this gives me this. Right, I'm gonna have a delta x squared, a delta x cubed, on and on and on and on. And by the way, I am taking the limit as delta x approaches 0, which means every one of these terms goes to 0 when I take the limit. What am I left with? Just that. Oh my goosh. The derivative of x to the nth power is nx to the n minus 1, which is one of the coolest formulas you will ever see in math. Quite literally, we brought the exponent down and decreased it by 1. You gotta admit, that is cool. Now, I only proved this for positive integers n. We are eventually going to prove this, by the way, for all real numbers n. We're eventually going to prove that this holds for every conceivable value of n, believe it or not, which is incredible. I only proved it for positive integers. I'm going to prove it for negative integers in a moment, and then next week I'm going to prove it for rational numbers, any fractions. We don't have that math yet. We will next week. So let's do a simple example of this, or some simple examples of this. All right. And I just want you to get used to also the notation. So if I said, find the derivative of, keep it simple, x to the 6th power, that would just be 6 x to the 5th. That's it. I don't need to do anything else. I do not need to use any theorems, any formulas. This formula we just derived will work for all positive integers in the exponent position. So one of the more practical things that we want to be able to do in this class is take derivatives of polynomials. So what if I have this? I want to take the derivative of this polynomial. But remember what I showed earlier. The derivative of a sum is the sum of the derivatives, which means I can look at this. I'm going to take that derivative plus that derivative plus that derivative plus that derivative. That's all I have to do. I don't have to look at it as one big thing. I do it one at a time. Okay. So everyone try this on your own for a moment. You don't have to blurt out an answer. Just try it on your own and see if you can get an answer. I am going to ask you to blurt it out in a moment, though.
Because what are we trying to do exactly? Like, I totally understand what you just said before, but how is that corresponding to this now?
Well, I want to take the derivative of this.
I understand that.
Now I want to take the derivative of this big polynomial. That means I'm going to take each derivative one at a time and basically just add them.
But this time they have coefficients. Before they didn't.
Yes.
So we just take.
But what did we show before? The derivative of a constant times a function is a constant times the derivative.
Right.
Does that make sense? So I'll write it out the long way. This is 4 times the derivative of x cubed minus 6 times the derivative of x squared plus 5 times the derivative of x.
I get it now.
Plus, if you will, say it this way, 4 times the derivative of 1. Now, I don't ever want you to rewrite this. I just want you to do this because you can. Now, we've just derived the derivative of x to a positive integer exponent is this. And earlier I derived that the derivative of a sum is the sum of the derivatives. The derivative of a scalar multiple of a function is a scalar multiple of the derivative. If I put all of those together, I can answer any question of this form immediately. That's the beautiful thing. I can answer it immediately. So this is what you're physically going to do. I want you to do that immediately. So what's the derivative of x cubed, anybody? 3x squared times 4.
3x to the second power.
Yep. So what's the derivative of x squared? 2x.
2x to the 1.
So times -6, that'd be -12x. What's the derivative of x? Of x to the
0.
first power?
0. A 1. X, because x to
1.
the 0 power
Good.
is 1. Yep.
Think of it this way. If I said the line y equal x, it has a slope of 1. Oh, so the derivative should be 1. That makes sense. So that last one is 5 plus 1. Now, the derivative of a constant. Ooh, we didn't talk about that. Well, if I thought of the graph of a constant, the graph of a constant is a horizontal line. What is the slope of a horizontal line always?
0.
0.
So the derivative of a constant is always 0. I'm not going to write plus 0. That's 0. That, by the way, you love derivatives of constants. That's the easiest thing you'll ever do. But a lot of times we forget because that doesn't seem to follow any rules. Well, what's f of x plus delta x? Well, the slope of a constant is 0. So the derivative of a constant would be 0. Remember, derivative right now is the slope of the tangent line. The derivative of this quantity is that quantity. And I can do this directly. Now, do notice something about my answer. All of the exponents decreased by exactly 1. That's very important. Notice that. Now, we're going forward. So for the next several weeks, I always say we're in the light, right? We're doing the light side of calculus, or call it the Jedi side of calculus. Around the middle of the semester, we get to what I call the dark side of calculus. See, we're doing the derivative. We're going forward. Later on, I'm going to start with this statement here and say, where did it come from? And which means you're going to go backwards. And that is called the antiderivative. It's like the dark side. Okay. That just sounds so, ominous. Turns out of all the things you learn, that's a number 1. Going forward is necessary because eventually we want to be able to go backwards and say, where did it come from? But that's not much different than in remedial algebra. When you multiplied out polynomials and you got one simple statement, then later you said, where did that simple statement come from? That's factoring. And that was a much higher level of reasoning, but you can't factor before you can multiply things out. You can't go backwards before you can go forwards. So we're going to get really good at going this way so that going this way will eventually become automatic. And I promise you it really, really will. So
Professor,
yes.
Is the reverse version of this called integration?
Yes. And the result is called the antiderivative. I hate doing this because I'm not an English guy, but there's verbs and there's nouns. The derivative and the antiderivative are the results. They are nouns. Differentiation is the process we did to get the derivative. Integration is the process you do to get the antiderivative. So integration would be the verb, just like differentiation. Does that make sense?
Yes.
But we won't be using that term for quite a while. That just gets confusing. So we've just derived a very, very powerful formula, but by the way, you never have to question. We just derived it. I didn't tell you it. So the next thing I want to do is I want to do the same thing for negative exponents, because what if we wanted to take the derivative of 1 over x to a power? I'd like to be able to do that. So here's what we're going to do next. All right. I want to do the derivative of 1 over x to the nth power for positive integer n. Okay, so I want to differentiate 1 over x squared, 1 over x cubed, 1 over x to the 10th power. Well, that's not the same thing. All right, this is not a polynomial. A polynomial has to have only positive integer exponents. This x is in the denominator. That makes automatically way weirder. So let's do it. It's going to be the limit as delta x approaches 0 of, now writing it out is a little bit trickier. X plus delta x, so it's 1 over x plus delta x raised to the nth power minus 1 over x to the n. Now, I believe on the worksheet that we worked on, I think we did something like this. In fact, William, I think you even asked the question when we were trying to manipulate it and eliminate that delta x in the bottom, we still had delta x's, but they were involved in a sum, not in a product. The algebraic manipulation of this is not trivial, but it's also not that difficult if I just have good bookkeeping. Now, remember, I don't want to spend a lot of time. I just want to write the answer. Right now, I have two different quotients within my numerator. So a common denominator of those two quotients would simply be that denominator times that denominator. So that's exactly what I want to multiply numerator and denominator by. We've done a problem of this nature before. This is the easiest thing I can do to get to my final result. I'm just going to multiply top and bottom by the common denominator that I would have had in the numerator. And then the next thing I get will be just one quotient, not a bunch of quotients within the quotient. That's just too messy. Okay, so right now, what do I have? Well, those will cancel and I'll have x to the n. Then those will cancel, so I have minus x plus delta x to the n. On the bottom, I have delta x times x plus delta x to the n, x to the n. Now, that term right there, this is not a problem. As delta x approaches 0, this is not approaching 0, right? Because that's x plus delta x. The problem, child, is that delta x. But you know, look at those terms. Doesn't that kind of look like the previous? What if I did the following? Remember, the derivative of a product is the product of derivatives, and the derivative of a sum is the, excuse me, I'm sorry. Limit, not derivative. Take that out. The limit of a sum of the limits. Everything I could possibly do to something I can do with the limits. I want to pull this apart, and I want to pull it apart like this. I want to factor out a -1 from the top and only have that term, and then multiply it, because the limit of a product is the product of the limits. So what would that leave if I do this? Well, I factored a -1 out of the top, and then the rest of the denominator would be here. Now, again, I said, if I cover up the word limit, is this quotient equal to this quotient? Yes, it is. Is this quotient equal to the product of these quotients? Actually, it is, because look at my numerator. If I multiply that by -1, I get this back again. And if I multiply denominators, okay, we're basically done. So how could we be done? This is just starting to get interesting. Because this right here, isn't that the derivative of x to the n? We already derived that. We know this. This is n x to the n minus 1. That was what we just spent several minutes doing. Now over here, this is cool. See this delta x? As it approaches 0, that term is just approaching x to the nth power. Which means this is approaching -1 over x to the 2n power. And folks, we have an answer. Now, this answer is kind of ugly. We're going to clean it up a little bit. Well, that's kind of, yeah, again, it's weird. All right, so I'll write it up here. What's the rule of exponents? I have x to the n minus 1 over x to the 2n. Aren't I supposed to subtract exponents then? So what is n minus 1 minus 2n? Wouldn't that be -n minus 1? Huh. By the way, can I rewrite 1 over x to the n as x to the -n? Is that legal to do that? Yeah. By the way, what did we just prove? If n is a positive integer, and I write it in this form, then I'm bringing down the exponent and decreasing the exponent by 1. That's exactly the same rule we did for this guy. So that rule of n x to the n minus 1 applies to positive integer exponents, and we just derived it applies to negative integer exponents. And I said before, it's actually, we're going to prove it applies to all real numbers. So here's what I'm going to ask you to do right now. I'm going to ask you to go out on a limb, and I want you to believe that this is true for every possible value of n, even though I've only proved it for integers, but I did prove it for positive and for negative integers. In a week, I will prove it for rational numbers, and then later we'll prove it for all real numbers. We just lack the tools to do all of it today. I mean, today is day one, by the way. So how does this work then? So let's do an example of this. I want to take the derivative of 1 over x cubed. Well, the first thing is I can't do it in that form. This is where we can get in trouble. I'm not going to differentiate that statement as stated. I'm going to rewrite this as I want the derivative of x to the negative third. Because now I can apply the rule. Oh, the rule says bring down the exponent and now decrease the exponent by 1. Now, we all agree that a negative exponent is not considered a simplified final answer, but it's totally okay to work with negative exponents. Meaning, I wouldn't say that's my final answer. I'm going to now rewrite this as negative 3 over x to the fourth. But if I didn't change it to this first, I might not see that that's the answer I'm supposed to get. And so that's why whenever you have something, you want to write it as an exponent whenever you can. Because if you don't do that, then it means you're probably doing too many steps in your head. And there's the potential for error there. I'm going to need a paper towel in a minute to wipe this down. So here's what I'm asking you to accept from this day forward. That the derivative of x to a power, no matter what the exponent, positive, negative, integer, fraction, square root, I don't care. It's n x to the n minus 1. This is an absolute formula now from this day forward. So I want you to differentiate the square root function. We already did this, yeah, but we did it using a limit. Can we do it straightforward like this? Well, only if we first rewrite it as x to the 1/2 power. If I first rewrite it as x to the 1/2 power, oh, now I can bring down the exponent and now decrease the exponent by 1. 1/2 times x to the negative 1/2 is just 1 over 2 root x. And that was a heck of a lot easier than doing a limit, wasn't it? You should like that. That was way simpler than what we did before. Okay. Now hang on 1 minute. I need a paper towel now. This is getting too messy. Unfortunately, my erasers can only handle so much. There's just too much backlog of ink now. So one thing I miss about being on campus is that I have boards that take up the whole room. So I don't have to retrace my steps that often.
Hey, Professor, I don't know if you ever do this, but I used to teach. And one thing that really helped me was with my erasers. If you like wash them, like under a sink and like kind of scrub off the ink and stuff and just let it dry, they work like new.
You're close. These things here wouldn't survive getting wet. Unfortunately, these are really, I got these from Platinum. So what I do, I do what you just said. I take the paper towel and I rub it really hard. But I get the buildup. You know, I've already done that once today. I will do that every day to my erasers, just like I wash this board at least once a day, if not twice a day, every day. It's not really a problem of anything. It's just the ink builds up. And when you're erasing it, the first round removes it. The next couple of rounds just smear it. You remember the old chalkboards? You guys remember those things? Yeah. I don't know if you had them growing up. If you erase a chalkboard enough times, what happens? You have this nice layer of chalk. It never removes the chalk. It just spreads the chalk out evenly.
Well, and also those dry erase markers have wax in them. That's what makes it so that you can re-erase them. So that wax builds up.
Yeah. So yeah, it's neither good nor bad. It just at some point I get a workout here. I mean, I am actually really pressing hard. Okay, so I want to summarize what we know and what we can use, because we have just developed some unbelievably powerful tools today that are extremely easy to use, because once you have a formula, you don't have to question a formula, you just have to apply a formula. So we have a formula that says if I have x raised to a power, I can differentiate it straight up. If I have a coefficient times that, I just have a coefficient times the answer. If I have a sum of things, I just have a sum of my answers. So let's do something maybe slightly more complicated. Now I'm going to write it because I want to get some formal notation in. Y equals, how about 3x to the fourth minus 5 over x to the third plus the cube root of x squared. I want to find dy dx. That means I want to take the derivative of all of this. Now, notation when it comes to derivatives, every calculus student who's ever existed struggles with notation at the beginning. It's like learning to spell a word in a foreign language. You got to, at some point, you want to get the spelling right so everyone else knows what you're trying to say. You may know the math, but you don't want to misspell the words, right? Because otherwise the next person may not interpret it the same way. I want to find this. That means I'm going to apply d dx to all of this. So I want you to get used to this. dy dx is the answer. That is the function. And it's equal to the operator applied. This is not a multiplication. This is an operator. I am applying it to all of these, but I don't want to write it in that form, do I? No. I want to write it as exponents. So I want to write it as 5x to the negative third. Then what will I write the last one as? Blurt it out if you know it.
X to 3 over 2.
Ooh, I'm glad you said that, because that's not correct. This is the one that gives us the most trouble. How do you remember? The root is always the denominator. So that's x to the 2/3, because the 3 would mean cube root. So that the roots give everybody trouble because the translation you do less of. Writing this as a negative exponent, you don't have to really struggle with that. But writing this as an exponent is a little trickier. And by the way, you have to write it as an exponent or you won't be able to find the derivative easily. So now I'm going to apply the differential operator to this quantity, and the next thing I write is the answer. There's no in between. So bring down the 4. 4 times 3 is 12, x to the third, one less. Bring down the negative 3. Negative 3 times negative 5, that'd be plus 15. Decrease the exponent by 1. Bring down the 2/3. Decrease the exponent by 1. Okay? Now, there's nothing about that that really should challenge you. Yes, you're going to have to practice. And there's a bazillion problems in every textbook that are just like this. Just do them. Do them until you get to the point where you can do them really fast and really accurately. Accurately is more important, by the way. Now, is this an acceptable final answer? Well, we would consider this to not be finished because I'm writing negative exponents. I need the negative exponents to do the derivative, but now when I represent my final answer, I'll represent it like this. 12x cubed, that guy's going to go downstairs. Now, x to the 1/3 cube root of x. Does it actually matter whether I write it as a root or a fractional exponent? As an absolute, it does not matter. A fractional exponent and a root are considered the same thing. One is not considered more simplified than the other. Now, because the original problem was stated as a root, I would probably be more likely to write that. But if you wrote it this way, absolutely correct. Remember, you had to go from root to fractional exponent in order to take the derivative. So you don't have to change it back if you choose not to. So either one of these two are absolutely acceptable because they're exactly the same thing. Okay, so that's a pretty simple process, isn't it? That's pretty slick. Now, what is a derivative used for? Well, we're going to do a lot of applications of the derivative over the next several weeks. What the derivative is, it's called an instantaneous rate of change. If I'm looking at a graph, the instantaneous rate of change of y with respect to x is equivalent to the slope of a tangent line. But if you're in a car, what's your instantaneous rate of change? It's your speed exactly at that moment of time. I'm climbing a hill. The instantaneous rate of change is what's the slope of the hill right at that moment in time. An instantaneous rate of change is a derivative. And we use them for all sorts of things, okay? We start with the slope of a tangent line to a graph because that's the easiest one to understand, and it's the easiest one to derive a formula for. But we go way beyond a graph. We can do derivatives for anything. We can do derivatives in higher dimensions. That's Calc 3, okay? So the next thing I want to ask is, can you take more than one derivative? In other words, if my derivatives are functions, can I take another derivative? Yeah, turns out in physical application, I'm going to use the simplest example there is because this will be one of the first applications. Motion. Okay, if I said I'm going to do, every moment I'm at a certain place, and I can even graph that, then the instantaneous rate of change would be my speed. The derivative of speed, turns out, is your acceleration. That's called the second derivative. And in reality and in motion, the second derivative is even more important than the first derivative when you're talking about movement and motion and things. It's really cool. We get heavily into that in Calc 3. Don't worry about that. But the idea is, how do you take a derivative of a derivative and how do you actually represent that? And so I want to do it from a notation standpoint. So I have y equals f of x. That's my function. If I do d dx to both sides, then we just simply say dy dx equals f prime of x. We generally call this the first derivative. In Calc 2, we have processes where you might have to take many derivatives to see if there's a pattern. So you might have to have 5, 6, 7 derivatives. And so how do you write that? So if I want to do the derivative of dy dx, well, what I'm actually asking you to do is the derivative of y. Okay, that's what we're actually doing. And we write this as, now this can be really confusing. I write it with the 2 on the top and on the bottom. Now, it does seem redundant that I put the 2 twice. And I can't really explain that in great detail until I get to Calc 3. The 2 on top means I want you to take 2 derivatives. The 2 on the bottom on the x says I want you to take them both with respect to x, as if you could do it with something else. Well, when you get to Calc 3, we have multiple variables in every problem. Oh, so I could take one derivative with respect to x and then the other derivative with respect to y. So in Calc 3, I can have more than one variable here. I can have an x, a y, a z. Okay, but in Calc 1, we can only have one independent variable. So these will always match in Calc 1. So that's the second derivative. We just simply write it this way. Well, what if I want the third derivative? Well, how would I write that? I'd say d3y dx3. Now, in this class, you're never going to have cause to take a third derivative, but you will do a second derivative very often because it's part of how we answer questions when we get to applications. Great, easy. So if I said the nth derivative, we just put an n there. Okay, that's kind of the general rule. Now, what about using function notation? So d squared y dx squared, this is called the second derivative. With function notation, we write it like this. Double prime. And we actually say f prime of x, here we say f double prime of x. Okay, that's it. Now, if that's the third derivative, then I guess I go like this. Oh, all right, now here's the problem. I want the 100th derivative. Do I, do you really think you'd be able to read 100 slashes? Like 1, 1, 2, 3. I have a bill that I get every month. I think it's my water bill. And my water bill, it has a number and then a long string of zeros and then more numbers. And every time I take my pen and I put a little, I'm counting the zeros. So when I write on my check, there's so many zeros. Yikes. Well, once you exceed 3, most people, it's too difficult to distinguish. So we write it like this. We just put it in parentheses up here. That's not an exponent. That means how many times you took a derivative. So when it's first derivative, second derivative, even third derivative, we use the little slash. Anything bigger, we'll just put the number there. Now, in this class, you would never have any cause to go bigger than 2, really. But in Calc 2, it is common that you're going to go past. And in Calc 3, when we do multiple, going past 2 is actually very common. So getting the notation is nice. Okay, so that's how I represent it with this type of notation. Now, again, that's about as far as we're ever going to go in here.
Are there formulas that take you straight to the 100th without going throughout the whole process of second derivative, third derivative?
It's kind of tough because there's so many different types of functions. Now, there is one function that you can shortcut to the end if you were doing an absurd number. Okay, but there's other functions. For example, with trig functions, with sines and cosines, there are certain patterns that we're going to show that where you repeat yourself. With exponential functions like e to the x, there are certain patterns. So yes, there are certain functions that I can fast forward because I know the nature of each one of the derivatives. And when that happens, you rejoice. Remember, you're never going to need to take 100 derivatives. But if I wanted to take 100 derivatives of x to the 100th power, there's actually a formula that I can write the answer. I'll give you a hint, it involves a factorial. Okay. But that's really special. And again, you're not going to need to do that. There's just no cause you're ever going to need to do that in this class. So what I want you guys to be able to do, if nothing else after today, is if I give you anything where I have an x to a power, that you could take the derivative seamlessly, but also you can represent it using the definition of the derivative, because there are certain derivatives that we haven't come up with a formula for. And so I still would use the definition. So I believe on your next quiz, or the quiz on this, I have one question where I'm saying use the definition of the derivative. That means you're going to use the limit. But then I've also asked you some questions to, just differentiate some quantities and just do it. Don't use limits, just differentiate them. So let's do one more simple example I'd like everybody to do. For y equals, let's say 6x to the 4th minus 3 over x squared plus 4 over the cube root of x to the 5th power minus 7. There we go. That's just evil enough. Now, the trick is don't try to answer it yet. You have to rewrite these guys as exponents because the risk is too great that you're going to get the wrong exponent. So rewrite these guys in the middle using exponents, take the derivative, and if necessary, simplify the answer by returning. So everyone try this just for a moment, okay? In fact, I want you to do it till the bitter end, your finished answer, and I am going to ask you, when you get an answer, wave at me and see and hold it up. You're gonna have to hold it up right up to your screen in order for me to see it. But this is something I would like everyone to, when you leave today, I want you to feel absolutely comfortable doing this.
You're standing like just in front of the first term.
Sorry. Well, you don't need this one. You mean you don't write fast? I'm standing in front. It's way up here. Okay. Not that tall. Or maybe it's, oh, the camera's at an angle, I guess. This part is very mechanical. There's no abstraction whatsoever. So when you think you got an answer, I'm going to go ahead and pause the recording for a moment in case it takes a little longer. So what's going to come next, now that we've learned how to do this part of the process, what about trig functions? That's one of the most important things. What if I had a product of things or a quotient of things? How would that work? Those are like the next couple things that we're going to do next week. What if I was working with something like a circle that's not even a function? How do you take derivatives if it's not even a function? Because if you thought of a circle, don't I still have tangent lines on a circle? Yeah, of course I do. But how would I take derivatives in that case? Because I can't even write y equals. So there's a whole lot of stuff coming up. Plus, then we get to the applications, some of them being very cool. You know, not only cool applications, but actually quite useful in general. So we're going to be doing a lot of mechanical stuff. We start with the definition of the derivative, and then we derive. So the next several weeks, there's not a lot of abstraction. Every time we derive a new formula, now we just practice using that formula over and over and over again. Now, do be mindful, I've posted a lot of notes. There's notes on definition of the derivative. I've already got videos out there, like videos how to do the trig limits. Now, to be honest, the trig limits on the last quiz, everyone should have got, because I did both of those problems in class, and I think I do them both on the video. You really can't, you shouldn't miss those, because the process, it's not that they're easy, it's that the process should be really, really comfortable. You know, and sometimes we have some goofy algebra. Now, what always concerns me, calculus, I mentioned before, calculus has the highest fail rate of any course at any four-year school. It has the highest fail rate at Mesa College. It used to be people would come into a calculus class and it was their first or second try. Nowadays, it is very unusual that I'll have a student who hasn't had calculus at least twice. Believe it or not, I'm not going to ask you, I don't want to embarrass you, but of the people in this room, I'm guessing there's less than 4 who haven't had calculus at least twice. I'm talking about high school also. You guys go, oh yeah, I had it in high school. I've already taken it once. I've already taken it twice. I've already taken 3 times the college level. No, there's people have all these repetitions, but a lot of times they don't change the approach. They just keep redoing it. But a lot of times you learn stuff in high school because maybe you were taking an AP class and they're showing you stuff. There are things you may have been exposed to that we haven't actually learned. Like, for example, yesterday's limits. I had people try to take a derivative to turn the limit, which means you really, really, really don't understand the process, because that's not an appropriate use. Plus, we hadn't even ever used the word derivative. So how can you take a derivative to find a limit? By the way, that's absolutely incorrect mathematics. You can't take a derivative to find a limit when you've just introduced what a limit is. The only time you take a derivative to find a limit, you haven't learned yet. My Calc 2 students will be learning that next month. They will learn how the derivative applies to a limit, and it only applies to less than 1% of the limits. You don't take derivatives to find limits in general. There's very specific ones, only ones that involve logarithms. And if you learned anything else, then you didn't learn that correctly. So eliminate derivative and limit. You know, do a derivative to find a limit. No. You can use a limit to find a derivative, but you don't use a derivative to find a limit. There is something you will learn, again, the middle of Calc 2 that involves derivatives, but it only applies to certain types of problems. And it doesn't apply to anything we will do this semester ever. So we want to get good at limits. Now, we're not going to do limits. We're done with limits. The only limits we're going to do the rest of the semester pretty much is to derive the next derivative formula. So we use limits today to derive the derivative of x to the n. And so we were able to do that. I could not have derived that without using the limit. Now, I introduced you to the algebra stuff with factorials and combinations. You can erase that from your memory now. I'm never going to ask you that. I introduced that at the beginning so I could show you when I did the expansion where it came from. If I had just done the expansion and started writing, combinations and factorials, a lot of you would have just been blown away saying, where the heck did that come from? So that's why I did the little bit of background. Most of you have seen that. It doesn't mean you know it today, but most of you have been exposed to that in another class. I just wanted to use that to show you when I did the expansion where the coefficients come from. And that's it. I never need you to know it again. We're not going to do that ever again in this semester, anything with factorials or that sort of stuff. Okay. But everything, we always want to justify stuff. All right. Let's go ahead and I'm going to stop recording now.